Hey guys, welcome to Stat 441 at Virginia Commonwealth University. In this lecture, we will learn about the continuous random variable and the probability distribution of a continuous random variable. So far, we have discussed the discrete random variable, but in many real life situations, in many experiments, the random variable that we observe is not a discrete random variable. That means the number of values are not countable, and such variables are called continuous random variables. Here are some examples of continuous random variables. The first one is the waiting time y in minutes at a traffic light. So this value of y could in theory assume uncountable infinite number of values in the interval from 0 to infinity. So positive value, but it can take any value. So therefore, y is a continuous random variable. A few more examples here. In each of these, the random variable can assume uncountably infinite number of points on the interval on the real line. So it could be one or more intervals on the real line. So here is an example. The daily rainfall at some location, okay, again continuous. The strength in pounds per square inch of a steel bar, or the intensity of sunlight at a particular time of the day. So all of these here are examples of continuous random variables. Now, when we have a continuous random variable, let's look at what the cumulative density function is for the variable y. So the cumulative distribution function is denoted by the capital letter F at y0. So this y0 could be any value of a random variable y. So the f at y0, the cumulative distribution function at a point y0 of this variable, our continuous random variable y, is the probability of y less than equal to y0. What that means is it's the probability that has been attained up to that point. Okay, so that's the cumulative distribution function, probability of y less than equal to some value of y, y0. Now let's compare this with the cumulative distribution function of a discrete random variable. So in terms of a discrete random variable, the CDF will be the sum, and we'll call it the cumulative sum of P of y. That means the probabilities added up to that point. When we say probability of y less than equal to a certain value y0, then we have to add all the probabilities up to y0. So let's say the discrete values are 0, 1, 2, 3, and 4. And let's say we want to find the CDF at 2. So we will add the probability at 0, 1, and 2. So probability at 0 plus 1 plus 2. That will be the CDF for a discrete random variable. Here is another look at a discrete random variable. So we know the binomial random variable is discrete. Let's say we have a binomial random variable where n is 5. Okay, so we have 5 Bernoulli trials, and the probability of success on each trial is 0.5. So based on what we have learned in the previous chapter, f of 0 will be, so C, the cumulative distribution function at 0 is probability of y less than equal to 0. So it's just simply probability at 0, which can be calculated as 0.031 for a binomial distribution. F at 1, the CDF at 1 is probability of y less than equal to 1. So we need to add the probabilities at 0 and 1. So 0, probability at 0 plus probability of 1, which is 0.188. Let's go further. When we get a 2, so the CDF at 2 is probability of y less than equal to 2, so we add 0, 1, and 2. Further down, for 3, we add 0, 1, 2, and 3. For 4, we will add up to 4. So probability of 0, 1, 2, 3, and 4, we add them, 0.969. And when we reach 5, that's the maximum possible value in this variable. So when we reach at 5, we add all the probabilities, and that should give us 1. Beyond 5, this probability stays at 1. So it's the cumulative probability up to that point. Okay. So for a binomial distribution, which is a discrete distribution, when we look at the probability distribution, this is what we can say. The CDF at 2, the CDF at 3, f of 3 is this shaded area. Okay, in terms of area, if we were talking about this probability density, then this would be the area below 3. Okay. Now let's make another graph, which we have the variable y on the x-axis and the CDF on the y-axis. So when we are at 0, we have the probability of 0.031. It stays at 0.031 until we reach 1, and then there is a jump at 0.188. Again, we stay here until we get to 2, and then at 2 there is a jump. We reach 0.5. Again, stay here, there's a jump. Okay, so the CDF here of a discrete random variable is a step function. So this is true for all discrete random variables. This was binomial, but this will be true for all discrete random variables. Once we get to the next value, then there is a jump, because at that point we add the probability at 1, we added the probability at 2. So this will be a step function defining this cumulative distribution function of a discrete random variable. Okay, and this kind of further explains that binomial distribution example. So the f of y is equal to 0.031 until y is less than 1. And as soon as it reaches y equals 1, we add that probability at 1. So probability of 0 plus probability of 1, which gives us 0.188. And then further jump and until we reach the final number, which is 5 in this case, and at that point, the probability is 1. So the number of jumps again will be the number of values the variable can take. So in this case, the binomial distribution, there were 5 possible values, and then the 6th is the final values. There will be 5 jumps to reach that. Now let's compare this to a continuous random variable and try to understand how is the cumulative distribution function f of y different for the continuous random variable. So the CDF for a continuous random variable is a monotonically increasing continuous function of y. What does that mean? That means that it won't be a step function. We will not have jumps, but it will be a continuous function, something like this. Okay, but here again, the probability starts at 0. Let's say this is where the function is true from 0 to infinity. So it starts at 0, and then the probability rises. At some point, it will attain the probability of 1, and then it stays at 1 for the rest of the values. Okay, so this is the idea of the cumulative distribution function of a discrete variable, which is a step function. And for a continuous function, it will be a smooth function. It won't be there won't be any breaks in the middle. Okay, this also means that the f of y is an increasing function. Okay, the probability keeps adding. We are not subtracting the probability. So if we have two values a and b, let's say a is here and b is here, then f of b is always greater than f of a. It's an increasing function. It is a non-decreasing function. Okay. Now, in terms of probability, we can understand the probability distribution of a continuous random variable, just like we did for the discrete random variable. So here is what we will do. There are three basic properties that are cumulative or the continuous random variable will follow. And then we have learned these probability rules. They should apply here as well. So the first one is that our variable y can take uncountable infinite number of values in the interval negative infinity to infinity. The CDF is f of y, the capital letter F of y, which is continuous, and the probability that y equals at any one particular value is 0. And this is something different from what we have seen in the past. I'll elaborate that in a few more slides. But the idea here is that for a continuous random variable, if you were asked what is the probability that y is equal to 2, and the answer is always 0. What is the probability that y is equal to 8? The answer is always 0. Because in this case, we will be treating probability in terms of area, and we need two endpoints to define that area. With just one point, the probability will be 0. Here is how we will define the probability for a continuous random variable. The probability will be defined with as a density function f of y. So now it's a lowercase f of y. The density function is, we can figure this out using the cumulative distribution function. So we differentiate the cumulative distribution function with respect to y to get the density function of our random variable y. So that's one way to do it. In most cases, we will be given the function f of y, and then we can integrate that function to calculate the cumulative distribution function. Okay, so here is how we will approach the properties of the density function for a continuous random variable. F of y is positive. It's always greater than equal to 0 because it defines the probability distribution. So it has to be positive. Then just like probability, the total probability has to be 1. So the integral of this function f of y with respect to dy is from negative infinity to infinity is equal to 1. So it's just like saying what is the CDF at infinity. So we know it has to be 1 because the total probability has been attained somewhere before that point. For finding the probability between two values a and b, like I said, for any specific value, the probability is always 0. So we need two endpoints. So let's say the endpoints are a and b. Then we can integrate this function f of y with respect to dy with the limits a and b. So that's one way to find it. If we know the CDF of the function, then we can use the CDF to find the probability. So f of b minus f of a will also give us the same value of the probability. Okay, so this is how we will treat our density function for a continuous random variable. So if we model it, this is what it would look like. On the x-axis, we have the values of y, and on the y-axis, we have the density function f of y. So this is how our density of the function of the variable y is varying. This is the bell-shaped curve or the normal distribution. So imagine this, you collected some data and made a histogram, and it gives you an approximate normal shape. So that's what this is. This will be the probability distribution f of y, and this will be the values of y. Okay. Now, in terms of so if this is the density function, then the area under the curve is the probability. So this total probability under the curve is 1. Okay, so we are thinking of in terms of area. So the total area will be 1, and then the proportion of area under the curve will be the probability. So let's say we have a value y is 0. Then what is the probability that y is less than equal to y is 0? Then it will be this area under the curve. Okay, and how we can find this? We can integrate our function f of y from negative infinity up to this point y is 0. That's how we can find the uh, probability up to this point y is 0. Okay, so it will give you a number between 0 and 1. Okay. We can also define now our cumulative area or the cumulative distribution function in terms of the density function. So just to keep the variables separate, basically, if you look at this slide, we want to find this area, okay? And our function is f of y. So instead of using f of y, because our limits are from negative infinity to y0, I'll use t just to keep it separate. So from negative infinity to y, if we integrate the function ft dt, that will give us the cumulative distribution function of our variable y. Okay, so that was some basic information. Let's put it together in an example and see how we can calculate the probability. What does the CDF look like, and what is the interpretation of these values? So here is the example. A cavity magnetron is a high-powered vacuum tube commonly used in microwave ovens. One brand of microwave uses a new type of magnetron that can be unstable when not installed properly. Let y be a continuous random variable that represents the proportion of these new magnetrons in a large shipment of microwave ovens that are improperly installed. Let C be a constant and consider the following probability density function for y. Okay, so in this case, we are already given the probability density function. This f of y is c times y, and this y is can take values between 0 and 1. It will be 0 elsewhere. Okay, so as you can see, y is the proportion of these new magnetrons. So its proportion is between 0 and 1, and therefore y is true between 0 and 1. Okay, so the first part is we need to figure out the value of c. How can we find that out? We know that this is a probability distribution, so the total area under this curve should be 1. Okay, what does that mean? That if we integrate this function f of y with respect to dy, and the limits are negative infinity and infinity, then this value should be 1. Well, in this case, we know that the function is true only between 0 and 1. It's 0 otherwise. So we can change the limits to 0 and 1. Our function is cy and then d of y. So y is the differential of the integral of y is y squared over 2. Our constant is c with limits 0 and 1. So when we solve for this, we get c times 1/2 is 1. That means c is 2. So our final function f of y is 2y. Okay. Next part, we need to, so this is what the function looks like if we draw it. So this is our variable y. It is true between 0 and 1. And the f of y is 2y. Okay, so at point 2, it's 0.4. 0.5, the value of f of y is 1. At 1, the f of y is 2. So this is what it looks like. And this is the total density. Okay. Now this area, this total area under the curve is 1. Okay. And let's say we want to find the probability between 0.2 and 0.5. Okay. What is the probability that the proportion of defective pieces is between 0.2 and 0.5? So it's this area. And the way we can find this is by integrating our function f of y between 0.2 and 0.5. So it's 2y. 2y, the integral is just y squared. Okay, y squared with the limits 0.2 and 0.5. So 0.5 squared minus 0.2 squared, that gives us 0.25 minus 0.04, which is 0.21. Okay, and what's the interpretation? So Y represents the proportion of improperly installed magnetrons, and we can say that the probability between 0.2 and 0.5 is 0.21. Okay. Now for the same function, let's also define the cumulative distribution function. So cumulative distribution function is the integral from negative infinity to y, and we'll call it the function ft dt. So we'll change it to 2t instead of 2y, and the limits will be 0 to y. Okay, 2t integral is t square over 2 times 2, which is just y square. Okay, with the limits 0 and y. So our CDF is y square. So basically, once we have the CDF, if we needed the probability up to a certain point, let's say we wanted to find the probability of y less than equal 0.2. So you just plug in 0.2 instead of the y, and we have the answer. So here's an example. Let's say we wanted to find f of 0.2 and f of 0.7. So f at 0.2 is just 0.2 square, because the CDF is y squared, which is 0.04, and f at 0.7 is probability of y less than equal to 0.7. Remember, it's the cumulative probability, so 0.7 square, which is 0.49. Okay, in terms of the figure, this is for 0.7. F at 0.7 means the probability up to 0.7. So basically the area under this curve, limits are from 0 to 0.7, but we've already defined our function. It's y squared. So we can plug in the value of 0.7, and that gives us this probability at almost 50%. So basically, the probability of finding 70% of fewer improperly installed magnetrons is 50%. So 50 here, and this remaining area should also be 50, between 0.7 and 1. Okay, so that's all for this lecture. Please watch the next video for calculating the mean and variance of a cumulative, a continuous random variable. Thanks for watching.